Good morning. Mic. Okay. What time? Good morning.
Good morning, sir.
Okay, respected dignitaries, distinguished faculty members, teachers, and dear students across India. On behalf of Rao Hall of Science and Education Technology Unit, I extend a warm welcome to all of you today's national level science outreach program, the chemistry concepts through interactive experiments, titled The Chemistry is Fun by Professor Uday Maitra. A special welcome to the students who are present here in person, Jawahar Navodaya Vidyalaya urban students, and all the students across India, under the Vigyan Jyoti, other STEM initiatives, and I welcome you all. And we are delighted to host this session exclusively for Jawahar Navodaya Vidyalaya under Vigyan Jyoti and broader STEM initiative. Today, more than 300 JNVs across all the regions of India they joined online. And we thank the Jawahar Navodaya Vidyalaya Samiti, for enabling and all the communication to all the regional offices and the beginning. I welcome you all. And this level of engagement reflects the growing reach of JNCASR outreach programs and outcome of the vision and leadership of our center. And we urge you to actively participate in the question and answer session at the end of the presentation. And you can raise the hands in the online participants. You can comment your questions in the comment box. You can unmute your the audio and the video, and you can directly interact with the scientist. Okay, and each school will receive the certificate at the end of the program and later this program. And now I request, it is my privilege to invite our colleague and Chair Education Technology Unit and Fellowship and Extension Programs and the great eminent neuroscientist of JNCASR and India, and Professor Shiba Vasu to introduce our today's speaker. Thank you, ma'am. Please.
Hello everyone, once again. It is my pleasure and privilege to introduce our distinguished speaker for today, Professor Uday Maitra. Professor Maitra is currently an honorary professor in the Department of Organic Chemistry at the Indian Institute of Science, Bengaluru, and he is also currently the president of the Chemical Research Society of India, CRSI. Professor Maitra completed his MPhil and PhD from Columbia University in 1986. That was followed by a postdoctoral research at the University of California, Berkeley. He briefly served at IIT Kanpur before joining the Indian Institute of Science in Bangalore in 1989, where he has over the last several decades made outstanding contributions to organic chemistry and also science education. His research spans several fascinating areas. They include the chemistry of bile acids, hydrogels, metallohydrogels and organogels, organic, inorganic hybrid materials, and photoluminescent sensors. His work has significantly influenced both fundamental understanding and also applied aspects of functional materials. Beyond his research, which he is eminently, in which he has done superbly, he is deeply committed to chemistry education and science outreach. He is a regular participant in outreach programs for school, undergraduate, college students, and is he is very well known across India for his energetic and engaging Chemistry is Fun modules, which you will also experience today. He has conducted these events not only within the country, but also across several countries in Asia and also other continents. He serves as a titular member of the Committee on Chemistry Education of the IUPAC or UPAC, and this reflects his international contributions to science education. We are extremely lucky and honored to have him with us today. Thank you, Professor Maitra, for your time. And students, teachers, please join me in welcoming Professor Maitra to today's event.
mic? That would help. Sure. I think I probably do not need a microphone here. I hope all of you can hear me, but it just makes the quality of sound better for the online participants. So I'll just take a pause for a minute or two.
Sir, 1 second. We are also very happy to tell you that Professor C.N.R. Rao, Bharataratna Professor C.N.R. Rao, who is really the person behind this event, this education technology unit, our engagement with the student community across the country over the past several decades, and he has joined us today. Professor Rao, we are starting the program now. Chemistry is fun with Professor Maitra. We are so happy that you've been able to join us, although only online. The students are also very happy to see you. Thank you so much for joining us, sir. And Professor Maitra is going to begin now.
Thank you. Thank you very much for the invitation and also for the very elaborate introduction, Professor Shiba. And I also thank Dr. Vinayak for keeping things in place in a very nice way. I will be engaging with you for 90 plus or minus a few minutes. So let me keep the timer on first. Before I begin, I would like to share with you a picture. Do any of you recognize this very famous physicist? Little louder. This is Richard Feynman. He said that understand, do not memorize, learn principles, not formulas. And this is the principle we will use today to convey the fun of chemistry. Let me show you a slide to indicate what brought me into this chemistry education programs. This is a Deccan Herald newspaper from 2002, I believe, 2004. By the way, before I formally begin, let me also welcome all the participants who have joined online. So hello everyone. So this was a newspaper article about an event that happened in Jawaharlal Nehru Planetarium at that time, some sort of a science exhibition, and I was shocked to read what is mentioned here. And this student, whose picture is probably shown on the left, said that I used to experiment with chloroform as I wanted to get into the subconscious mind. This is a highly powerful state of mind where you can memorize quickly. Now nothing can be further away from truth because chloroform is toxic and it can kill you. So I ended up, those days the communication was through fax. All right, so most of you do not know what fax is, but I was able to communicate to the editor to contact the reporter and tell her to contact the student, okay, to convey that he should stop doing all experiments like this. Let me, before I begin, acknowledge the people who have helped me organize this one. My research group, in general, they helped me in packing things. Dr. Vinayak and also two of my students. Please come forward. Nandita, raise your hand, and Simpa. They are going to help me. And I would also like to thank Dr. Palani from Merck Sigma Aldrich because he is very supportive of this chemistry education program and he supplies me with some more expensive chemicals. So this is chemistry is fun. And I have two words here, SDG 4 and SDG 17. I will explain to you what it is. And this is actually number 103 in the series. We completed 102 2 days ago in Farooq College in Calicut. So I'm very pleased to be here. Now let me start with a question. What all colors do you see here? Other than yellow. Red, green, blue, white. Black, of course. Okay, black and yellow we will not consider. Now suppose what is the importance of red, green and blue? They are called the primary colors, you all know. Suppose I mix red, green and blue paints. What color do I get? White? White is correct? Pigments, paints, red, green and blue. I'll get black color, because what we see as a color is actually the reflected light. What appears blue implies that it absorbs red light. What appears red implies it absorbs blue light. So if I mix these three, they will absorb all the light. On the other hand, if I mix radiation of red, green and blue color, what do I get? Now we will get white. We will do that in two different ways towards the very end of the experiment. We will start from there and gradually progress it to this. If you get bored, you can leave, we can stop. But the last experiment will be the most exciting one. And we will make white light by two different means. One is by using light, one by using chemical energy. I will also show you that if you mix these three pigments, you get black color, okay? Because you need to know both the things. Let me now go to the next very important slide, and this is a dedication slide, and I would like to dedicate today's number 103 presentation to Professor C.N.R. Rao and Srimati Indumati Rao. And here's a picture, Professor Rao, perhaps you can recognize. This was the last FCBS meeting in Trivandrum, and you and Mrs. Rao were probably on the way or on the way back from the temple visit in the morning. So thank you very much for supporting chemistry education in this country in a big way. I'm very pleased to be here today. To see Professor Rao is watching us, keeping a close eye on us. Today is November 28th, right? Anybody's birthday today? Anyone? Raise your hand. Whoa, one of you. Very nice. Every day in the year, okay, or every day, something interesting has happened in the history of science, in the history of chemistry. Let's see what all happened on November 28th, other than that this being your birthday. First pure compound of berkelium, which is element number 97, was announced based on the work done by University of California in Berkeley in 1962. Then Hyatt was born in 1837, who actually discovered a very different type of a plastic called celluloid, which were earlier used for making camera films, which again your generation has not seen. Another very important, perhaps one of the most important scientists of the world, Antoine Lavoisier, it is a very, one can give a 1-hour lecture. Professor Rao has also given many talks, including that about the life of Lavoisier and his contributions. But I will simply say that he surrendered himself to the revolutionary French government in 1793 on this day. That was a very bad, very sad day for the history of science, because eventually he was executed for his scientific activities which were against the church and also for opposing some of the government actions. Last but not the least, Alfred Nobel obtained a patent for smokeless gunpowder in 1887, and he made a lot of money from which the Nobel Prize is given. So to celebrate the birthday, the events on these 4 occasions and your birthday, we will do a small experiment here. This is a balloon which is floating in the air. Let me ask a question. Why is the balloon floating? Helium. What else? Hydrogen. What else? No air. Air will sink. Right? What else? Any specific gas you can think of? Methane? If you know gas laws, molecular weight, methane is lighter than air. And the 4th example is neon. Okay. Now let's assume that this is only hydrogen or helium. what experiment shall I do to find out whether it is hydrogen or helium? Okay. If I ignite it, helium balloon will just burst, whereas hydrogen balloon, okay. So let's do that experiment. Now assume that each balloon has a size of, I will not burst the big one, okay? And I can assure you that as long as you are 6 feet away, you are absolutely safe. We have done it hundreds of times. So everything should be about 6 feet away. Maybe I'll do it on that side. Is there any sensor that side? No. Over there. I think this is fine. This is fine. Let me take it away, further away from everybody. All right. 3.36 liter. Keep in mind, because every experiment will come with a question. Yeah. Let me first get the flame away from me. Huh? No, no problem. It will only produce some water. Uh-oh. I think we'll manage. Maybe it is the draft from the AC. This is an experiment Professor Rao also used to do. So Professor Rao, here is, move back, and we will do it with only one balloon. The rest of the balloons we will do. Just a second, I just need to be, it's okay. Okay? I prefer, shall we do it inside? Okay, bring the smaller one. Bring the smaller one. No smell, no sensor activity. Okay. Bring the smaller one. Are they together? Okay. So right here there's a small one. Okay, bring it here. Bring it here in the same location. Keep it here. Thank you. You need to focus there. Can you do that? Okay. So Simpa, you light the candle. Okay, move back, and I will slowly do it. Again, 3.36 liter. Why I am saying this is important. Done? Okay, so this is very safe as long as you take safety precautions. Professor Shiva, are you okay? Okay. How about you? You're okay? Oh, everybody is safe, right? No smoke alarm, nothing. So my question is, in fact, when I don't have this available, I would typically do it with a video, okay? And let's do that. All right? So the question is, you forget 2.24, assume this is 3.36 liter. So the question is, I burnt hydrogen gas, it produced steam. You don't see water. Because of the heat, it will produce steam. Suppose we condense the steam back into water. What will be the volume of water obtained from 3.636 liter of hydrogen? I think those of you who have studied gas law should be able to find this answer. Now I would like to show a few slides, because this is very important, because we are in 2025. If you think about Mother Earth, can we have these lights dimmed so that you can see the screen more clearly? If we think about Mother Earth, what is it that we get from outside? It's only the sunlight, right? Nothing comes in, nothing goes out. Earth has 8+ billion people now, okay? And every human process utilizes energy and increases disorder. In other words, we take concentrated minerals from different places, use them, and then distribute it as waste. And we do not get things back, usually, right? And therefore, putting this back into an ore form will require a lot of energy. So you must have read about 3 R's: reduce, reuse, recycle. Of these 3 R's, reducing and reusing do not require any energy consumption, but recycling does. Any recycling requires energy input. We take a lot of pride in installing solar panels, right? India has installed capacity of several gigawatts, I believe, or tens of gigawatts. But then you have to remember that these solar panels have a life of about 15 years. So what will happen after 15 years, we don't know, because the recycling of solar panels is a technology that is not yet developed. And we don't have land where these things can simply be dumped. Okay, so this is a question that your generation will have to address. And therefore, our motto should be to reduce waste generation. In addition to reduce, reuse, recycle, the 4th R would be refuse. If somebody offers you more than what you need, you should refuse that. And that can lead to a little bit of, reducing the consumption. I would also like to show you something that is listed here. Remember, I indicated SDG 4 and SDG 17, and that refers to the Sustainable Development Goals of the United Nations. I don't know how many of you are aware of it, but there are 17 Sustainable Development Goals announced by the United Nations, and in many of them, chemistry is involved in addressing the concerns. And number 4 is quality education, which is part of our today's activity, plus number 17, which is partnership for goals, because JNC, JNV, I'm from IISc, these institutions are now involved today in getting across to you a different way of looking at chemistry. And chemistry has a solution to all of them. And I would also like to introduce to you another terminology called systems thinking. When you study subjects, you study in science many sub-areas like physics, chemistry, biology. But think about it. Whatever we study is for understanding nature. And nature does not care about physics, chemistry, biology, mathematics, anything. So while we study nature, we need to understand that we need to understand nature as a big system, not isolated as physics, chemistry, biology, mathematics. Again, your generation will be responsible for addressing a lot of problems which I have indicated in the previous slide, the United Nations Sustainable Development Goals. But solving any of these problems will require a systems thinking approach. You simply cannot be a chemist and try to solve all the problems of the world. So there is something called systems thinking, sustainability, and systems thinking in chemistry education. And this is a website. I will not go into the details, but I would probably like to play a small video which indicates what is expected from the future generation. Audio?
Modern societies face several global challenges, including ending hunger, guaranteeing access to clean drinking water, fighting new and re-emerging diseases, reducing greenhouse gas emissions, and achieving sustainable development. Addressing these issues will require the collaborative actions of citizens and professionals who can understand these problems and are prepared to respond and manage complexity and rapid change. Chemical knowledge, reasoning, and practices can and should be used to confront challenges related to, among others, agriculture, health, energy, and climate. But to better equip current students with the knowledge, skills, and dispositions they will need to contribute to these efforts, chemistry educators must take immediate and definitive actions to align curricula, instructional methods, and assessment practices with these ambitious goals. The complex nature of the issues to analyze, understand, and confront demands that students meaningfully understand central ideas in chemistry, know how to apply science and engineering practices to investigate phenomena and design solutions, develop systems thinking skills to analyze the systems of interest, and act with socio-environmental responsibility. The systems thinking approach to chemistry education provides a unifying framework for learning and understanding chemistry as more than a static body of knowledge, but rather a dynamic and powerful way of knowing, thinking, and acting to build a safe, healthy, and sustainable world.
I hope this short video gave you an impression about what systems thinking is and how you should combine your knowledge in different areas to understand problems which are really in front of us. I have been asking questions to you, right? I have already asked one question about the amount of liquid water from the balloons. Asking question is very important, because scientific investigation usually starts with a question, not with an answer. All of you are very good in answering problems, right? Questions in the exams. That's what is expected. But what is important is not answering questions, but asking good questions. If you don't believe me, let me show you the quote from somebody. This is Heisenberg. Some of you might have read about Heisenberg's uncertainty principle. Heisenberg also made the statement that what we observe is not nature itself, but nature exposed to our method of questioning. In other words, nature will only give you the answer based on what question you ask, and therefore it is very important that you ask the right questions. I will give you one more example from this gentleman. You may recall that when you are very young, maybe first, second, third standard, and you come back from school, and whoever is at home would typically ask you, what would they ask you? How was your day? What did you study? How did you do? This gentleman says, not my mom. My mom would say, did you ask a good question? And then he goes on to say that difference, asking good questions, made him a scientist. And who was he? His name is I.I. Rabi. He discovered something very important, got the Nobel Prize in Physics in 1944. And have you heard about MRI? MRI based on a principle called NMR, and that is what he discovered, nuclear magnetic resonance. Okay? Now, asking question is one thing. Answering question also requires a little bit of understanding. Perhaps none of you have heard about Occam's razor. Have you heard? Anybody? No. Occam's razor is a principle which says that if you have two answers to the same question, always choose the simpler of the two. Okay, here is a different version of the same statement. Okay? And another point that I learned from my college teacher is you have to remember the principle of ABC. What is A? Your answer should be accurate. B, answer should be brief. And C, answer should be clear. Okay? So in most Indian languages, including Hindi, it is satik, sankshipt, spasht. So 3 S in Hindi. That is something you need to keep in mind. Now let me ask you a question. How many of you are from 12th grade, 12th standard? Some of you, not all of you perhaps. There is a very important principle you have read, very important reaction you have read. That reaction is carried out in this reactor, chemical reactor. This is an old chemical reactor made by Nobel laureates. It makes something that 40% of it is in your body. Okay? Whatever has been made in this and other reactors, 40% of it is in your body, and it basically has helped humankind survive during the last 100+ years. What is it? Any guess? Okay, if there are no guesses coming right now, I will try to give the answer at the very end. It was made by 2 Nobel laureates, one chemist, one chemical engineer. Chemistry is a central, creative, useful, and what is called a connecting science. It connects many disciplines. I will skip some of the other details. For example, chemistry is in food and health, housing, clothing, transportation, quality of life, environment, and even in computer revolution. 35 plus years ago when I started my career, my laptop had a hard disk of 20 megabytes and a clock speed of 16 megahertz. And you know what your smartphone, if you have one, what the storage is, what the clock speeds are. Okay? It is because chemists have developed materials. Material chemists have developed materials which have superior properties and storage and everything. So what's everywhere? Chemistry is everywhere. Let's put the letters together. Indeed, chemistry is everywhere. And let me try to show you one example. I think this is a sandwich that I had to eat in a flight a couple of weeks ago. If you look at do you look at the expiry date of any perishable food? You should, you must. But you should also look at what the ingredients are, because there is a lot to learn from the ingredients and also from what the components are. If you look at the ingredients, there are some numbers called INS 260, INS 202, INS 211. Do any of you know what these numbers are? Little louder? No. It's very important that you know, because you can learn a lot of new chemistry out of it. Let me list a few, but I will leave a few for you to find out later on. Okay. And for example, these are called E numbers or International Numbering System, INS. These are approved food additives. They can be color, they can be stabilizers, they can be emulsifier, acidity regulator, and so on. Like 260 is acetic acid, vinegar. Okay? 150 is caramel color. So in these sandwiches, when you see a beautiful brown color, typically it's not wheat bread. It's not made from wheat, but it is actually colored flour, okay, with caramel. You need to keep some of these things in mind. So I'm leaving most of the numbers without any description because I want you to do that as a homework, okay? But you also notice something that the Indian population should be aware of whenever you buy a packaged food, such as a popular brand of noodles, I don't want to name it. They contain, typically it will have about 25 to 30% of your daily requirement of protein, carbohydrate, and fat. But sometimes the amount of saturated fat that you get just from one sandwich is half your requirement. And the amount of salt that you get is way too high. I think even for your age group, if you eat just 2 sandwiches, you have already consumed all the salt that you require to eat. Okay? So be careful about some of these numbers, especially when you are eating packaged food with high salt content. Now what is this? This is a Mars rover, name Perseverance. Okay? Now I'm sure that all of you are excited by these planetary missions, including the Indian planetary missions. They're exciting because you fire a rocket from a bit bigger than what you use during the festivals, and they reach the planet, lower the robot. This is actually a robotic car which you control from the Earth, and it does all kinds of things. Now it requires a lot of engineering, a lot of physics to place it on the Mars surface, let's say. But why has it been sent there? What are all these equipments? Let me explain to you what these equipments are supposed to do. These equipments are mostly sent there to study the chemical analysis, generate a chemical profile of the surface of Mars. For example, this equipment called MOXIE is a way to find out if carbon dioxide from the Mars atmosphere can be converted to oxygen, because if people go there in the future, they will require oxygen. Similarly, this spectrometer is used for the detection and analysis of chemical elements. So therefore, the primary objective of all these planetary missions is actually to do chemistry on another planet to find out if life exists, or if the chemistry is suitable for sustaining life in the future. Okay? I will give you one more example. This is a picture of the surface of Titan. Apart from Titan watches, Titan is famous for another one. This is a moon of which planet? Saturn. So there was a mission called a Cassini mission. I will just try to wrap it up right now. But what I'm trying to show here is that this is from the Cassini aircraft, spacecraft. This unit called Huygens probe was fired into Titan, and before it crash landed, it took a picture, but it also did a lot of analysis using this equipment. And you can see this in this instrument, there are all batteries around it, but in the center there is an instrument. It's called a chemical instrument called GCMS, gas chromatography and mass spectrometer. That was used for measuring the profile of the atmosphere of Titan before it crash landed on the surface and took this picture. Okay, time for experiments. I think I have given a lot of gyan to you from the slides, but there will be a lot of fun. Beginning now. Chemistry often looks like magic, and sometimes you may have experienced but perhaps not realized that the magicians use a lot of physics and chemistry to do their experiments, to do their magic, but they won't tell you the science behind it. Okay? Some of the experiments which may look like magic today, I will explain everything, okay, so that you are aware. So I will ask Simpa and Nandita to, and then we will recycle this. Don't show it. We will reuse this tissue paper. Again, for sustainability reasons, we try to reduce and reuse things. Hold it here, up, same height. Okay, that's good. Now, if I were a magician, I would say nothing is written here, but obviously something is written. Okay, and I have this yellowish liquid. I'm going to spray it, and this is a very safe experiment. But just to be on the safer side, we have both of them, Simpa and Nandita, wearing glasses and wearing gloves. So let me see how the spray works. I think the flower will be safe. Okay, move it up a little bit. So this is the title of today's presentation. Chemistry is fun. This is all chemistry. One liquid, one yellowish liquid, two different colors. That means we must have, or they must have written these things with two different chemicals, and this is the third one. So can you identify the three chemicals? I hope I have not, I don't have it up on the slide yet. This is not a pH. This is not anything to do with a phenolphthalein or colors. This is transition metal chemistry. Okay, you will read more about transition metals in your 12th grade. Okay, thank you both. You can stick it, I think there are some already cut pieces of tape. You can stick it there so that it stays till the end of our presentation. This is ferric chloride, FeCl3. And let me show you the chemistry. Chemistry is very simple. The letters which turned blue, and in fact that blue color is called Prussian blue. That was used as a pigment in the 16th, 17th, 18th century. That was written with potassium ferrocyanide, whereas the ones which turned into maroon were written with potassium thiocyanate. And this is the chemistry that happens here. Incidentally, potassium ferrocyanide also has an INS number. It's an approved food additive. And therefore, there is also this is something very interesting, because you all know that potassium cyanide is a poison. It's a very, very strong poison. But when it is complexed with iron 2, it becomes non-toxic and it is used as a food additive. And I would like you to find out what is the purpose of potassium ferrocyanide as a food additive. Okay, let's go to the next slide. You might have observed that I'm wearing a special tie. I don't like wearing ties, you know, in this weather, don't feel comfortable. It's a periodic table tie, okay? Periodic table is the most important table in chemistry. But periodic table is not completely chemistry, because even though we have 118 elements known so far, unless these elements form a bond, there is no chemistry. Chemistry is all about making and breaking bonds. You notice that we actually made bonds, broke and made bonds when we blew up the hydrogen balloons. We made new bonds when we made this banner, right? Because different bonds have been formed. So chemistry is all about making and breaking bonds. Now, there is a special type of a periodic table. You might have seen or come across many types of periodic table. The most modern form of periodic table dates back to 1869. Who was the discoverer? Mendeleev, right? In 2019 was declared by United Nations as the International Year of Periodic Table, and we did a lot of activities at that time. Now I will tell you about a periodic table that has been launched by IUPAC in 2016. It's called Isotopes Matter, www.isotopesmatter.org. In this periodic table, as I mentioned, it was launched by IUPAC in 2016. You hear about isotopes of elements and what they do for you. For instance, let me go to the next slide. This is a mummified body found in the Austrian Alps in 1991. And using a combination of isotope effect studies of different types, they were able to find out, for example, let me go back one step. For example, where Otzi was the name given to this mummified body, where he might have lived both as a child and as an adult. Okay, for example, if I analyze any of your dental enamel and the nails for hydrogen, deuterium, oxygen 16, oxygen 18, I'll be able to find out whether you are from the Himalayas, whether you grew up in Himalayas or you grew up in Chennai or Bangalore. Okay, so all these things you can understand by looking at these four and many more panels on this website. Let's do a simple experiment with isotopes. What are the isotopes you are aware of? Carbon, hydrogen has 3 isotopes, right? Okay, tritium is radioactive, so we can't use it here. So let's do some experiment with D2O, heavy water and water. Now, suppose I give you, it is called heavy water because it has a density of 1.1. Get a piece of paper ready because I'll give you a small problem. Suppose I give you a small amount of H2O, maybe 1 spoon. What experiment would you do to distinguish between H2O and D2O? What experiment do you think you can do? One is to measure the density. Okay, let's see whether we can measure the density. Yes, I have a small balance here. Okay, we will try to do it both ways, and I'll use this as a piece of paper to write things. Any of you have a pen? But then if I measure the density here, none of you would be able to see what's happening, right? So let's do an experiment then. Let me ask you this. H2O ice, that is water ice, floats on water, right? So will D2O ice float on D2O? It should. But what about D2O ice and H2O? Turns out D2O is 10.5% heavier than H2O but ice is 8% lighter than water. And if you do a small calculation, you will realize that T2O ice has a density slightly more than 1. So what we have done, I need some ice water here, thank you. I will pour some ice water here. And what we have done is we have taken small samples of H2O and D2O. My students, including Simpa and Nandita, they are sometimes they can be very naughty because I don't know which one is H2O, which one is D2O. They have only made one little bit green in color and one is orange color. Okay, these are using food colors. So let's see which one will float, which one will sink. That's the idea. Okay. All right, I'll take the challenge. And why do I have ice cold water? Oh wait, but then we are supposed to do the density measurement, right? So I have exactly 3.2 ml of each. So can one of you write down, you come here, on the piece of paper that Professor Shiba has given. So I'll take the weight of the filled one, weight of the empty one, and that difference will roughly give me the density because it's the same volume. So write down orange container. Oh, I have to switch it on. Orange one is 4.96 grams. Okay? And the green one is 5.51 gram. You know, the syringes themselves can be different, so can be different, so they can have different weights. So this weight doesn't tell you anything. So what we are going to do is to drop these ice pieces into the water in the measuring cylinder, and I will explain why we have used ice cold water. Okay? All right. So Simpa, you will be helping me with the first experiment. Or Nandita, you come here, because Simpa is busy writing lab records. Okay, you hold it at the bottom. So let's go green first. Okay? Let's go green and see what happens. It is still rock solid, so I have to warm it a little bit more. Let me save some battery power here. Okay. All of you can see this, right? See, measuring density is accurate, but you won't see what I'm doing. But now you should be able to see what's happening. So I'll now push the ice, and it happily sinks inside. That means this is D2O. So I will record the weight, and Simpa, you write down the weight of the empty green syringe is 2.14 gram. Okay? All right. Now the next one. Next one must be H2O, unless you have used D2O for both of them. You know, this little piece of ice costs about 300 rupees. So D2O is expensive. And I'll put the orange ice now. And that, of course, does not go inside. Thank you, Nandita. Thank you, Simpa. Oh, we have to measure the density. 2.03. Okay? So now you can check the weight of these two. Weight of the D2O? 3.37. What of the H2O? 2.93. Okay? Which means that 3 ml of water, approximately, these weights are approximate, about 3 grams, whereas the D2O weighed 3.3 grams, which means indeed that was D2O. So you can see that H2O is floating, D2O has gone down, but why did I use ice cold water? That is because D2O melts at 3.8 degrees, H2O melts at 0 degrees. So let me ask you, which ice will melt faster? Orange ice or green ice? Orange ice, you are right, because this is close to the melting point, whereas the water is ice cold, so this will melt more slowly. But then, as the D2O ice melts, it will produce a layer of liquid D2O, green color. And the remaining part of the D2O ice will start floating or dancing between the D2O and the H2O layer. So I will keep this one here. Nandita, you keep an eye on it for about 4-5 minutes, and then we can continue with the other experiment. So this can be removed now. Okay, keep an eye, and once it starts to dance, you can take it around. Now the next experiment is going to be a bit of a mess, but we are ready to tackle it here. All of you perhaps have seen an experiment called the elephant toothpaste experiment. You have seen it. Okay, that's how I used to do the experiment. But now that experiment has evolved into something that I call chemical sculpture. Okay, and I'll tell you what it is. Chemical sculpture, if you search, you will see these sort of things outside the chemistry departments of many Western universities. But this experiment is really an experiment on catalysis. Hydrogen peroxide is a second compound between hydrogen and oxygen, other than water. Water we made already. So now hydrogen peroxide somebody has made for us, and that is an unstable compound. It decomposes into water and oxygen. But it doesn't happen very fast. But this reaction can be speeded up by adding a catalyst. Sodium iodide acts as a catalyst. So that's what we will do. But to make the experiment a little more entertaining, we will mix some liquid soap It has got a slight blue color, but that's okay. I think that is fine. And can I get the hydrogen peroxide bottle? We'll take it from the fresh bottle. Is it from a fresh bottle? The one we used from the lab did not work all that well in St. Francis School last week, earlier in the month. You check? Anyway, I will use the JNC hydrogen peroxide. Thank you. This is 30% hydrogen peroxide. It's very corrosive. It will make your skin white. So this is soap and hydrogen peroxide. Okay, nice. Okay, let me secure this bottle. And I will now divide this into 3 equal portions. And I will tell you why. Approximately equal portions. 1, 2, and 3. Are they equal? Roughly. Okay. Now here comes the RGB story. To one I add the red food color. This is called orange red color. Second one I add the blue color. By the way, this orange red color is actually a mixture of yellow and red. Again, these have E numbers. One is E110, one is E129, I believe. Similarly, the green is not a single color. It's a mixture of blue, which is E133, and E110. So I add the green color. Let's be a bit generous. And finally, we put the blue color. You know, blue food color is a little hard to get. You know, you don't see too many blue food, naturally occurring blue food, other than blueberries or jamun and things like that. Okay. So, each of them goes into one measuring cylinder. So, this is R, G, and B. This is actually 2 experiments in one. I'll tell you what the second experiment is. Let me mix it. I have to be absolutely careful because this can make my fingers burn. Okay, now we can add sodium iodide and be in business. But then, if I now add sodium iodide and it starts evolving oxygen, does it prove that iodide is the catalyst? I think it doesn't. Sodium can also be the catalyst. Right? I add sodium iodide, which has sodium ion and iodide ion. I'm claiming iodide as a catalyst. But sodium can also be a catalyst. How do we prove? By adding a different sodium salt. So here is sodium. Yeah, you can now see, let me just go back one step. The D2 ice has partially melted, and you can now see, I will hold it tight here, and you can focus, Praveen, you can focus here at the bottom if you can see it. The D2 ice is floating between the green D2O and the nearly colorless H2O. I think, Simpa, you can take it around and along the aisle and show it to the students. Now, I can add sodium iodide, and as I said, I will add first the sodium acetate here, and there is no activity. Then I add another sodium salt, sodium bicarbonate, baking soda. Nothing happens. I will quote a dialogue from a very old and popular Hindi movie. Ye bhi bach gaya. Which movie? So before I add the third one, let's hear a clip. Oops. Okay, it's not working for some reason. Okay, doesn't matter. Now we will add sodium iodide. Okay? And for that I will take one more beaker from here, or a conical flask. And I take this good amount of sodium iodide, dissolve it in some water. Simpa and Nandita can now come back. You know, I could have all the things prepared and brought it here, but I prefer to show everything in your presence so that you see that there is no magic that's happening here. And then I will ask Vinayak, yes, Dr. Vinayak, also to join. What's your favorite color, Vinayak?
Green color.
Green. Okay, so you are green. Simpa, what is your favorite color? Between you can choose only between blue and red. Red, come here. And Nandita, you are left with no option, blue. Come this side. Yeah. So hold your test tubes here. Okay? Nandita, Simpa, and Vinayak. Okay? We will do a 3, 2, 1 count. 3, 2, 1, fire. Here comes our multicolored elephant toothpaste, or it will produce a sculpture, a modern sculpture. Okay? And this sculpture is different every time I do it. And you can see that, oh, it's overflowing a bit, but I think we should be able to contain it. And you know, this is a crowded room. we are consuming a lot of oxygen. So the purpose of this experiment is also to make some oxygen out of hydrogen peroxide and make the air more breathable. So you can see the sculpture being formed. I will rotate it slowly. There's a little bit of a spilling here, and you can see that the beautiful edges, and every time it is done, it is different. Okay? So this is a beautiful abstract art, so to speak, right? Thank you. Matchbox. How do you know that this is oxygen? This will support combustion. Let's see whether that happens. Okay? Now, this is not the best way to do it, but you will see that it brightens up. It doesn't get extinguished, but it becomes more bright. And sometimes if you have a bigger an agarbatti and things like that, if you insert it, it will burst into flames. Okay? All right, so I think this tray is just about enough to contain it, and you can see this multicolored sculpture once again. Let it stay here for a little while, because we will now, so Nandita and Simpa, you know that this one and the three beakers, they still contain some hydrogen peroxide, so they have to be cleaned very carefully, washed with water, only with water. But then I told you that red, green and blue colors, when mixed together, I need the colors. It will produce black. So let's do that experiment. So this is by mixing pigments. Okay? So I put a little bit of green. This is just arbitrary amount. Red. Oops. I spilled again some, but that's okay. You can see that it is already looking dark. And then I will put some blue color into it. You know, depending upon the quantities added, now you see it looks a little red, but if I use them in the right proportion, it will become black. At least it is not turning white, right? Because it is absorbing everything, it actually looks pretty much black. Okay? You can come later and take a look at it. All right. But then the other experiment is still waiting for us. That is, we mix radiation of the three colors, and we will see white light coming out. Okay. We will now take a bit of a pause, a short pause, and very little D2 ice now still floating. The H2 ice is already gone. Let's leave this thing here, and you can start cleaning it up from this edge. We will need the hydrogen peroxide again for the last experiment. Okay? And we created a bit of mess, but I think this is okay, because everything is on this plastic surface. All right. Let me go back to the slides now. As I mentioned, that until elements form bonds, you do not have chemistry. You have to form and break bonds. All of you are familiar with the Lewis dot structure for making bonds. So that type of bonding was first discovered by G.N. Lewis. And the very fundamental paper, of course, chemical bonds have been forming and breaking for billions of years. But the first clear understanding, particularly of the covalent bond, was given by G.N. Lewis, who actually worked in Berkeley. And that paper was published in 1916. And I will use a very simple, pictorial, almost child's description of bonding. If I have a small hand and a big hand, the bonding is weak. Okay? Because the handshake is not good. Physical handshake. Such examples are between a small nitrogen and, let's say, big iodine. If I mix iodine and nitrogen, if I form a bond between nitrogen and iodine, it's very weak. The energy is, as I said, about 40 kilocalories per mole. If I have two hands of the same size, strong handshake, strong bonds. I give you some listing of CF, CO bonds, they are very strong bonds. Now what does this number tell you? 38 or 40 kilocalories per mole. Yeah, but how does it connect with something that we eat? You know, each adult, you have not reached that stage. Adults require about 2000 kilocalories per day. How much energy do we get from carbohydrates, proteins and fat? 4 calories per gram of fat. Correct? No. You should correct me if I am saying anything wrong. 4 kilocalories per gram for protein and carbohydrates, 9 kilocalories per gram of fat. That's why fat is called fattening. Okay? All right. So 40 kilocalories is like 10 grams of sugar or 2 spoons of sugar. Okay? That's how you should always connect what you study with the real life numbers. Now, I would like to show you this example of Ni3. Imagine a small nitrogen having 3 big iodines around it. Okay? 3 very weak bonds. So anything with weak bond is packed with a lot of energy. And it is so energy rich that it is very shock sensitive. Shock sensitive means that if you touch it with something, it will explode. And Ni3 is a very unusual molecule in that sense. I will show it only on a video because it is not safe to do it here.
When nitrogen triiodide, the dark-colored solid, is dry, it is very sensitive to touch or any vibration. Simply touching it with a feather causes it to explode or detonate. One detonation causes another to occur. One product of the reaction is violet iodine vapor.
So you saw that instead of throwing a cracker on the ground, you can simply, if it is made up of Ni3, you can simply touch it with a feather and it will explode. But my question is, if it is so shock sensitive, how do you keep it on the filter paper? Think about it. This is a question for which I will seek the answer from you at the end. Now I notice that I have less than 30 minutes. I have already used up 1 hour, so I need to move fast. Another type of weak bond is called hydrogen bond. You all are familiar with hydrogen bonds, aren't you? Hydrogen bonds are very important in life, primarily because water is a liquid at room temperature because of hydrogen bonds. H2S is a gas. Hydrogen bond also keeps our proteins in the proper conformation, in the DNA in the right helical shape. Coming back to water, as you know that water is heavier than ice. And this picture on the left-hand side gives you an idea that when water is liquid water, has a lot of weak hydrogen bonds. But when it freezes, it expands and forms very well-defined hydrogen bonds, as you see on the right-hand side. It is like a diamond-like lattice. You might have done this experiment when you take a bottle of water like this, keep it in the deep freezer. What happens? Water forms ice, volume expands, the bottle gets distorted. If it is a glass bottle, breaks. Let's do it with an iron container. Not here, on the video. So we will take a small iron container, fill it with water and freeze it very rapidly using dry ice and acetone, which is at -78.
The ice bomb illustrates the fact that the volume of ice is greater than the volume of an equal mass of liquid water. Some cold water is poured into a cast iron bomb, and a threaded plug is screwed into the bomb so that the bomb is tightly sealed.
And this is dry ice acetone.
The bomb is then placed into a dry ice acetone slush, which is at -77 degrees Celsius, and will cause the water inside the bomb to freeze. A wooden box is placed over the top of the bomb and slush bath. It takes a short time for the water to freeze. When it does, the bomb explodes. Some of the dry ice acetone slush is blown onto the explosion shield. Little bits of the cast iron bomb are left. When the water freezes, tremendous pressure is produced. The pressure is enough to cause this cast iron bomb with more than 1/8 inch thick sides to burst.
Can we have the lights dimmed right now for the next experiment? It is easy to break weak bonds, but sometimes it is very important to break strong bonds. For example, carbon dioxide, which you hear a lot about these days because we have too much of carbon dioxide in the atmosphere, which is causing temperature rise, global warming. It would be nice to be able to break this bond, and I will show you how it can be done. Okay, and so you have seen magnesium ribbon burning? Most of you have seen that. And here is some magnesium that is kept between two blocks of dry ice. Have you heard about dry ice? It is solid carbon dioxide. Okay, so here's the video.
Magnesium is placed in a cavity in a block of dry ice.
So this is magnesium
The
chips.
magnesium is ignited.
You ignite it with a Bunsen burner and cover with another block of dry ice once it starts to burn.
And covered with another block of dry ice.
So the burning magnesium does not have any oxygen around it or air. It's all CO2. But you see what happens.
Despite the absence of air, the magnesium continues to glow due to its reaction with carbon dioxide. Because of this reaction, carbon dioxide cannot be used to extinguish magnesium fires.
Not just magnesium, any metal fire, like lithium battery fire, you cannot use carbon dioxide. You have to use a dry powder extinguisher. Keep this in mind. Let's see what's inside.
The reaction products are white magnesium oxide and black carbon.
And I think you can write a balanced equation. And what magnesium has effectively done is to extract oxygen out of carbon dioxide. Exactly what we require now. But the catch is that magnesium does not occur free in nature. Okay, you have to put that much of energy to isolate magnesium from its ores, like calcite, dolomite, and magnesite. What about breaking nitrogen-nitrogen triple bond? That is also very strong, 227 kilocalories per mole. Okay? I've already given you a hint, but I will come back to this. Now, I will do one small demo on reactions. This is for those who are in 12th grade or higher, well, 12th grade, because you might have read about SN1, SN2 reactions. If I ask you which one will react fastest in SN2, I have a primary bromide, secondary and tertiary. SN2 reaction, primary will react fastest. SN1, everybody knows that, okay? And you also know the reason for it. But has anybody seen this reaction? We could have done it, but it will take some time, so I will show you on a video. Okay? So let me show you. And the principle here is very simple. The reaction, when it undergoes an SN1 reaction in the presence of a alcohol, for example, okay, here, it produces HBr. And how do you test bromide? Has anybody done bromide, chloride, iodide test in the lab? It is done with silver nitrate. Okay, so the demo is, I will speed up the demo because there are 3 containers with methyl alcohol, and we will add the silver nitrate solution to all of them. Okay, so that is done. I will speeding it up, and then add the primary halide here. It has been done. Secondary and tertiary. Watch it now. As soon as the tertiary bromide is added, you see a precipitation, and that is because of formation of HBr. So therefore, primary, secondary is turning little bit cloudy, but the tertiary immediately formed a precipitate, confirming that it has reacted very, very rapidly. Okay, we could do this reaction here, but then it will take much more time than what we had left with. So I will skip this part. Okay, I will skip this one also. I have this magic glass, but I'm feeling very thirsty. Can I have some water? Lights on, please. Can you get me some ice, please? Some water? This water will do. Get me some ice. I think this water I can drink, right? It's not cold enough. So add some ice. Keep the oxalic chloride straight. Pour more. Okay, all of it. Okay. Oh my God. Something is not right. Either the water is bad or the ice is bad. Which one? Water is bad? Water is turning red or the glass turning red? How do we confirm that? What experiment do we do? Pour the water out, exactly. You know, this is the simplest experiment because again you apply Occam's razor. That is the simplest answer. Let's see. Indeed, water is fine, ice is fine. Glass has turned red. But now you see something that looks like magic. I hold it this way, remove my fingers. So the glass has in it, the plastic, some chemical which turns red below 10 degrees. My hand, my fingers warmed it up, so you see the color disappear. And these are called thermochromic substances. Okay. So we have another set of thermochromic substances because it's very important to show this slide here because I will tell you the reason in a minute. This is a silver salt of HgI4 and a copper salt. They have different colors. Banana painted with a silver salt which is yellow in color, apple painted with a copper salt which is red in color. That's why we painted banana and apple. So, simple. You heat this one. Make sure that everybody gets to see what's happening. Is it on? This is our desi style of using a 3-point pin. So just warm it up and you will be able to see that the yellow banana is getting more ripened. Has it become orange? I can't see it from this side. It has become orange. Oh, very good. But then it is reversible. Okay, wait. It is reversible. It will again turn yellow below 50.7 degrees. This happens with the silver salt. Copper salt, you can see that already I change silver to copper, it becomes red from yellow. And let's heat it stronger. You bring it closer. It's turning black. So what happens? It is turning black. Little closer. You can see that it requires a higher temperature and it is getting rotten. Beautiful red Himalayan apple, maybe Himachal Pradesh apple is turning, oh no, I think as the temperature drops down, it becomes beautiful apple again. But this doesn't happen with real apple. Okay? It would be nice if that would happen. Oh, I messed it up here again, but you can put this to back. Now the reason I said it is very important to show it in JNC, it is because a very young and dynamic researcher here, Professor Kanishka Vishwas, he has found out why these two molecules change colors because of the change in their crystal structures. Okay? All right. Setting sun and blue sky. What causes this? Scattering of light. When light passes through the atmosphere, short waves get scattered and we see the sky in the scattered light. If you go to the moon, the sky will appear black because there is no atmosphere. And when we see the setting sun, we see the light from the sun after the blue light has gone. and the short waves are gone. So therefore, we are left with the red. I will show you something with lights in the next two experiments. All lights off, please. All lights off. What you see in this picture is the longest river, second longest river in Europe, called Danube. Okay, Danube is here, and this is a river called Rhine. And people believe that Rhine and Danube are connected underground. And what they did, they put a fluorescent molecule here, and after 3 days, they found it in a tributary that connects to Rhine. So fluorescence is a technique by which light of one wavelength becomes converted into light of another wavelength, okay, and longer wavelength. And that is called fluorescence, and you might have seen many fluorescent molecules, okay. So fluorescein is one such molecule, but the first molecule for which fluorescence was discovered is called quinine. And let us do some experiments with fluorescent molecules. And I have listed in the next slide. So what we will do is that we will shine light of one wavelength and we will see emission of a different color. And we will use these 4 chemicals. You might say, where do you get these chemicals? Okay, answer is very easy. On the top left, you have quinine. And quinine comes in this can of Indian tonic water. Okay, this was invented, so to speak, by the British, okay, because quinine was, at that time when the British came here, only drug against malaria. So they started drinking quinine infused water, and of course they started adding other things, but that is not relevant today. So this is quinine. So we'll put quinine here. Top left, let me ask you a question. What is this? I told you ABC. What is this? Highlighter again. So if you want to answer accurately, you have to say pink highlighter, yellow highlighter. Simpa and Nandita, put some water in each of them. And I will put some tonic water in one of them. Okay. So this is tonic water which is bubbling because it is a carbonated drink. Okay, nobody drinks from here, okay. So this is top left, quinine. This is pink highlighter. This dye is called solvent red 49. Put little less water, okay. And that is fine, that is fine. So I'll stir this. This is a very strong color, like fluorescein. And then, what about this fellow? What about that fellow? Where is our ingredient? Right here. Some of you might have taken these capsules, vitamin B complex capsules, okay? And this is typically given when you are taking an antibiotic, when you are feeling weak. This contains, the B complex contains many B vitamins, including this, which is vitamin B2, riboflavin, and that is also a fluorescent molecule. So I take this capsule, nothing fancy, okay, you can buy it for 2 rupees or less. I break into one of them, get some water. So this is like a powder because it has got all the vitamins, some other solid, something else, I don't know what. But we will extract the fluorescent molecule out of it. So 1, 2, 3. My time is really a little bit on the lesser side, so I'll need another 5-10 minutes, if that's okay.
Yes, sir.
All right. So this is going to be filtered now. Filter into one of these glasses. And Nandita, you hold the torch because I need to see what I'm doing. And I will also blank the screen. All lights off, please. Do it. No. That's what you are here for. Okay. Oh, that light we cannot control. Okay. Doesn't matter. Now, this is quinine. This is pink highlighter, green highlighter. And then I need some lights, monochromatic lights. For that, I have a red laser pointer, okay, a green laser pointer, and a purple laser pointer, RGB. All right. So let's first start with red. No fluorescence, but you see it is transparent, it is not absorbing the light. Because when light passes through a medium, it can be absorbed, emitted. Here also there is no light that is coming out. You see a little bit of a scattering here, okay, because the yellow highlighter also has some solid material in it. Now the green laser. As expected, this is showing scattering of green light. Okay? This showed scattering of red light. This shows scattering of green light. Okay? No surprise. Quinine, little bit of scattering. Pink highlighter. Now 1, 2, 3. So you see that this pink highlighter ink is fluorescent, and here is a proof that it is only the pink highlighter extract that is showing the yellow color, but the one below that is only showing scattering. So the transmitted light is still green, the absorbed light is emitting at a different wavelength. And then Simpa is ready with the extract of vitamin B complex, and we will add some more water to make up the volume. That's fine. And as before, we do a little bit of red laser and green laser. Okay? Now the fun part. Quinine is fluorescent, I mentioned, right? And here you see the beautiful cyan fluorescence from quinine. Okay, I've got some soda and some Sprite, but in order to save time, I will not show that. Those two will not show such fluorescence because this has quinine. This is again the yellow fluorescence from pink highlighter. And why do I have the yellow? Now you see yellow becomes green. And vitamin B2 shows a different shade of yellow. Now you can see both of them are different. One more. Okay, now that's fun, but you see this is blue, this is yellow. Blue and yellow are complementary colors. And I will now mix the pink highlighter ink with tonic water, make a what I call a Maitra mocktail. So here we go. Blue and yellow, and shine the laser. What should it give? White. Right? So I mixed this and this. The top two are mixed, and at the bottom you see a different color. So, and then I also told you that the yellow highlighter and the B2, vitamin B2, they show very different colors. Both appear greenish yellow, but this one This is from vitamin. It looks more yellowish than green. And this is a very important property of fluorescent molecules. You can detect the amount and the nature of the molecule by looking at fluorescence. Our eyes cannot distinguish them so clearly, but you can put these solutions in a spectrometer, and each of the fluorescent molecules we have a signature, it's like a fingerprint. So by this, a lot of molecules in food, in medicine, in cosmetics can be detected and their concentrations determined. Okay, so I hope that you appreciate the Maitra cocktail that we made here. Okay, there's a white light emission. But let's do something even more interesting. And then the most interesting part is the last set of experiments. Get me the 4 conical flasks. We are slightly out of time, but then we will try to manage things. So this is basically what we did. Okay, green light through the pink highlighter gave a yellowish emission. Purple light through quinine or the same solution gave a greenish emission. Through the yellow, blue light through the yellow highlighter gave a green light, and through B1 or B2 gave a slightly yellowish green emission, whereas through quinine it gave the blue color. Red does not give anything, and then we mix these two to call, Maitra mocktail. This is the first white light emitting mocktail actually, and that gave white light emission. All right, last experiment. We converted light into light in the previous experiment. Now, can chemical energy be converted to light? Yes, the fireflies do it. There are many types of worms which also do it, and that is called bioluminescence. So the chemical name is chemiluminescence, and that's what we are going to do. And our old friend hydrogen peroxide is going to be our fuel or energy. That chemical energy we will generate or harvest by mixing it with a very nasty molecule called oxalyl chloride, but we will use a solution, small amounts, so that's fine. And we will use 4 fluorescent molecules to give 4 different colors. This molecule, you don't need to worry about the chemical structures. So this fellow will give you a sort of a bluish violet light, orange yellow light, cyan, and green. And once again, we will mix these two to generate white light. But let me blank the screen. No, let me have the screen light a little bit so that I can see what I'm doing. I need some tissue paper. Okay, it's right here. And again, I'm trying to speed things up. 2 droppers, please. And dichloromethane is here. Yeah, thank you. So I will allow me just 2-3 minutes to set things up. And I have my old, no, I will use my favorite spatula. This is I call it my $1 million spatula. And I put the first compound from your left-hand side to this. We are creating a mess, but that's okay. So that is for the blue-violet color. Yeah, it's good to have a little bit of light here now. Number 1, and to avoid contamination, I have to wipe this. And I put rubrene in the next one. This is rubrene. And these are the chemicals which Dr. Palani from Merck Sigma Aldrich supplies, so that I can show the experiments without worrying about the cost. And the third one from your left is perylene, which will give the cyan color. And last but not the least, what looks like 2 naphthalines stitched together, that is called tetracene. That is the most expensive part. That will give you a green color, but that may stay only for a very short time. Okay, so that's basically the preparation time, and we are now in business. Let me put this one back, and I have to dissolve these into dichloromethane, which is not yet banned in India, but it is banned in United States, or getting banned in United States. But we are using it very small amounts, and it's cold. So it doesn't have too much of vapor coming into the room. Okay, so that is only for dissolving the materials. You can put it back. And do you have the waste container here? Yeah, keep it ready. So we'll do first experiment only on these two, and one of you can get ready with the torchlight. And maybe that you can give us, bring out the hydrogen peroxide bottle from our container, because it's a smaller in size, easier to handle. Yeah, leave it open. And I'll put a dropper inside. Thank you so much. Thank you both. Okay, all lights off. You be ready with the torchlight. You stand here, and I will blank the screen, because we are going to generate light. All right? Unfortunately, that window we didn't think about. I will first add oxalyl chloride. No, I think we don't need the torchlight, because there's enough ambient light. Are we ready? Okay, so blue-violet on your left and yellow on your right. Okay? And this is cold. This is not hot. All right. So, I will now mix these two, and it should give a orange light first, then white for a short time, and then blue again. This is a little tricky part of the experiment. I need to mix it in the right proportion, and just by adding a little bit. You see white for a short time, and then it will become blue again. It's almost white. It's slightly bluish white, but this color will disappear and become blue again. Okay, and this light is usually, if I do it in a completely dark room, this light is bright enough. You see this has become blue again? All right. So now the last two parts of the experiment will be now done here. Oxalyl chloride and hydrogen peroxide. So this is cyan and this is green. You can pack these two. Okay, cyan on your left and green on your right. This is perylene and this is tetracene. You can therefore see that not only can you convert light of one wavelength to light of another wavelength using molecules, but you can also convert the chemical energy, this time all coming from hydrogen peroxide, into light. Okay, and the reason why these things look different is something that you need to learn, and you will learn it when you study photophysics. So this is our small contribution to make a solar spectrum, starting from blue-violet all the way to orange. Okay, going through cyan and green. Okay, so that is the end of the experiments, but I need to use a few more minutes of your time. I hope that's okay, to illustrate to make a few more points. Okay, one of them is to talk about this scientist. He was the only, so far he is the only scientist who got 2 unshared Nobel Prizes. One in chemistry, one in peace. Any guess? His name was Linus Pauling. I have a video, but that will take too much time to play here, so I will skip that. But in this video, I would like to make 2 statements. One is that he was working on the protein structure. Remember I showed you a right-handed helical structure of a protein, which is called alpha helix. Those of you who are in class 12 may know. So alpha helix was discovered by him when he was in a hospital bed. Okay, he didn't have anything. He just had a piece of paper. So he started drawing the structure, started folding it, and discovered alpha helix. So that's one important thing, that when you are looking at a problem, if you are trying to solve a complex problem, you should never give up. Second thing is that in this video he also says that when he was 13 years old, a friend of him showed him 3 chemical experiments, and he was so impressed, he decided to become a chemist then and there. I have shown you about 7 experiments. I hope that there are some Madame Curies and Linus Paulings in the audience who will take up chemistry for your career. As I said, that never give up if you're working on a difficult problem, okay? This is one such example. Other thing is that always keep your eyes open, because as Pasteur said, chance favors the prepared mind. Nature presents a lot of problems at you. Unless your mind is ready, you will not be able to exploit that. So keep your eyes open, except while sleeping. So this is a problem. Just to tell you that you have to keep your eyes open. I saw this peculiar drawing in our campus while walking one day, and I thought this is an ancient drawing of a human figure. Do you agree? Is there any, apply Occam's razor? Yes. From a different angle it looks like OFC, which is optical fiber cable. Okay? So this is kind of only for some sort of on a lighter vein, but then the point I'm trying to make here is that, try to find a simple solution to a complex problem. That's where many new theories, many discoveries are made. Don't find a complex answer to a simple problem. I said chemistry is everywhere, and now my effort is now try to take chemistry everywhere, okay? And I will show you some pictures from my earlier events. You all are familiar with IUPAC, right? Here is a picture organized by the IUPAC. He was the IUPAC president at that time. We did one show in Cape Town, and you can see little girls spraying ferric chloride to create a celebration banner on the right hand side. This is in Jayanagar for not so young people. This was a couple of years ago in Kuching in Malaysia. Again, blowing up balloons in Malaysia in a different location. This was, I'll skip through some of these. This was in IIT Kanpur last year, in Mysore, Kumaun, Doon School and Doon University last year. These IISc, again you see that my toothpaste experiment has become chemical sculpture. This was in Turkey earlier this year, and this was in IISc Trivandrum about a couple of months ago, and this was on 1st of November, and this was just 2 days ago in Kozhikode. This C is for chemistry, okay, so we should take a picture like that. And the space is reserved for today's photos here, okay? So the pictures that we take here today will go in here. Wait. Where next? My next interest is to do it next to the Persevere rover, okay? And if you think this is a joke, I have a boarding pass here. July 2026, and if you are interested, you can log into the NASA website, go to Mars mission, pick Perseverance rover, and generate your own boarding pass. So see you all in July 2026. That's not all. Another minute or so. How many of you have heard the periodic table song? Anybody? Or only a small number. So this was a song composed by a Harvard University mathematics professor. His name was Tom Lehrer. And he composed a song out of all the elements known at that time. And later on some animations has been provided. So I have two versions. I have an animation, and also I have one which is Tom Lehrer singing it. But maybe the animation will be more entertaining for this group of students. So I will play this song. You can actually get up, start singing and dancing. You can come to the stage if you want and start dancing with the song. But here it is.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercurium, molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, titanium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Thank you. Thank you very much. You know, I must say that whatever I presented today is all based on known knowledge. I have only put them together, so I don't really deserve any credit for this. But I really would like to thank all the people who made this possible. My students, Dr. Vinayak, Professor Shiba, Nandita, Simpa, and also support from Dr. Palani of Merck Sigma Aldrich. With this, I would like to thank you again. I hope that I have been able to illustrate to you that learning chemistry can be a lot of fun. It's not simply based on what you read in your textbooks, which can be very descriptive, but chemistry can be learned in a much, much better way. Wait a second, I'm not done yet. What is this reactor? This reactor makes ammonia out of nitrogen. This is the Haber process. I'm sure you have read it. This reactor was built by Haber and Bosch. It was used for 55 years and made almost 800,000 tons of ammonia. And it is kept as a monument outside the biggest chemical factory in Germany called BASF. Okay? That was the ammonia reactor. Then the next question was, how much liquid water? Not 2.2, 3.4 liter. Huh? 3.36. So did you have an answer? 1.6 is not, 1.6 what unit? Whenever you describe quantities, don't forget the unit. 1.6 liter. 1.35 grams is too less. Okay, I'll give you the answer. You try to back calculate. It's about 2.7 grams. Okay? Because what you have is 0.3 mole of hydrogen. 3.36 liter roughly is 0.3 mole because 1 mole of hydrogen will be 22.4 liters. Right? So, 0.15 mole actually. 0.15 mole will be 3.36 liter. So 0.15 you multiply by 18, that's about 2.7. Okay, Ni3 is shock sensitive, so how do you keep it on the filter paper? Remember, during the festivals when you buy firecrackers, if it is a rainy day or a wet day, what do? You wait for the sun to dry it. So water is a spoiler in all these firecrackers or gunpowder. Because water has a high specific heat, it takes away the heat when it starts to explode. So Ni3, when you make it as a water suspension, and then you keep it on the put it on the filter paper, and then wait it to dry, and then you come back with a feather. Okay? All right. So thank you all very much, and see you next time. Thank you.
Thank you.
So we have time for some questions. It was a very exciting lecture demonstration. I'm sure you all enjoyed.
Sound good.
How about some questions? Who wants to ask any questions? Go on.
And online comment on made. Can you switch on the online comment?
Anybody?
I'll pin made.
Anything is okay. every question is welcome.
Including the questions which you might think are stupid questions.
Exactly. There
The
is
stupid
no such
questions
thing
are only
as-
those which you do not ask. It's an old joke. Okay? Yeah, wrap things up.
Online audience, if you wish to ask a question, you can raise your hand or you can
Put it in the
unmute
chat
yourself.
box.
Yeah,
Put
you
it in
can
the
put
chat box.
yourself. Yeah. No, we could ask them to unmute and ask also if you wish.
Yeah, I can probably close the presentation here.
Bangalore, you guys should ask first. Yes? Anything is okay. Remember what Professor Maitra said, asking questions is the most important thing. And young people should be full of questions. People like me.
Yeah, as we have been saying, that asking question is when you learn things. Getting the answer is easy. It so happens that, you know, nowadays many students, they do not try to go for the answer. They only are looking for 3 wrong answers in an MCQ.
Yeah, there is a question. Okay.
Yeah.
Oh,
Can you
great.
pass this?
Hey,
Very
let's
good.
clap for this person. Woohoo.
Hello, sir. Sir, my name is Shravan Kumar Mahana. Okay. So I think it might be a stupid doubt, but we have been learning throughout the ages that atoms can neither be destroyed or be created.
Say that?
Atoms.
Huh.
So how did they come at the first place? So, yes, sir. We have been learning that atoms can neither be created nor destroyed, but how are they present?
Who created the atoms?
Yes.
We don't know. We don't know. We know that the universe existed,
Okay.
and we are only playing a very, 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 very small role.
Okay.
Because, you know, you might have seen the picture of Earth taken by Pioneer 10 before it left the solar system some decades ago. And Earth is just a small point. And we are incredibly fortunate to be present in this huge empty space. But we don't know how the empty space was created and how the planets were created. We know how things get transformed. But how atoms were created in the first place, we don't know. Because everything seems to have been created from hydrogen and helium.
Yes.
Okay. But how those elements were created, we don't know. I mean, what is the universe?
Just made out of
Okay,
atoms.
this is more of a philosophical question. We are only trying to explain things that we observe in nature, but that is a much more fundamental question for which I don't think anybody has any answer and anybody will ever have an answer.
Yes. During even earlier, the people used to think that Earth was they used to think about geocentric model, that Earth was the center and everything revolved around it.
Even if you say that XYZ created the Earth,
Yes.
okay, then you have to find out who created XYZ,
Yes.
right? So this question will never be solved, I believe.
Okay. Thank you, sir.
Okay, thank you.
Any other question? But these are valid questions, you know, because particularly children at your age should have such questions.
Excuse me, sir. My name is Sejal, and I had a doubt. In glow sticks, they have some kind of material in them. When we break them, they start to glow, and after some time, the glow doesn't stay.
Which state?
Glow sticks, sir.
Glow
sticks.
Glow stick, huh?
Yes,
Glow stick is
so-
nothing but chemiluminescence.
Is that harmful for us?
As long as you don't break and take the liquid out.
But I did that once.
If you break it and take the liquid out, it can be harmful because we use hydrogen peroxide for many of these, and they use a different form of hydrogen peroxide. Okay, and that's not good for your skin because that is an oxidizing agent. Because no matter what glow stick it is, there will be an oxidizing agent, something that is rich in energy. Because ultimately you are converting chemical energy into light energy.
Yes.
In the glow stick, typically there are 2 compartments, 2 components, and when you break it, when you bend it or break it, they get mixed, chemical reaction happens, and then they have a fluorescent molecule like the one of the 4 or there are many others present there. Don't break it and don't get it on your skin. Just enjoy the glow
Thank you, sir.
and dispose it off properly.
Nice. The questions are hotting up
See,
now.
there is always a what is called an induction period.
Inertia.
Okay, small inertia, so you don't ask question, and then when somebody asks question, it goes up. Third one.
How does the radium emit light?
How does?
Radium.
Okay, this is a much more complex question. Sit down. This is not your classroom. You don't have to get up to ask questions. Radium has a nucleus. You know, as the number of protons in the nucleus increases, I must admit that I am not a nuclear scientist, not a physicist, so I can give you only an approximate answer. So radium and many other radioactive elements, they have more protons in their nuclei as the atomic number increases. And they are all positively charged, so even though you have some neutral neutrons, they still repel each other. So they start to break. They emit an alpha particle, some of them, which is basically the nucleus of helium. That way, they reduce the number of protons. These alpha particles, when they pass through the atmosphere, they ionize molecules, and it is the ionization of the molecule that leads to emission of light. It's basically the nucleus is disintegrating. It emits energetic particles, though that energy ionizes the surrounding molecules. Some may be particles of air, molecules of air in the air, and it is because of electronic transitions in those molecules you see light emission and the glow.
There is a question from Adya of JNB Pune,
Yeah.
and the question says, does the bioluminescence remain intact even after the death of an insect, or does it get degraded?
Okay, this is a very good question, because you know the chemical reactions happen in all biological systems as long as they are alive. As soon as an insect or any other organism dies, all the chemical processes stop, and therefore the chemiluminescence will also, or bioluminescence will also slowly but surely disappear after the insect's death. Good question.
Thank you, Adya, for your question. Any more questions in the online audience? You can type your questions in the chat box or unmute yourself and ask the question.
Okay, here is one from the audience.
Audience
Sir, my
question.
name is Gagana. Blast in Red Fort is due to which chemical, sir? Blast in Red Fort.
Blast in Red Fort.
Yes, sir.
No.
That's a secret. No, though, these are typically explosives which terrorists have used, and typically there are many types of explosives, but you know it's not ice bomb, right? Obviously, TNT was an explosive that was made long back. Okay, TNT is not used for this. There is another type of explosive which is very, I would say, popular. That is called RDX. It could be RDX, it could be many other explosives. There are many types of explosive, and typically the explosives contain a lot of nitrogen and a lot of oxygen. Because if I am using a cracker, most of this cracker require combustion with oxygen to generate the heat and explosion. That in most explosives, you have an oxidizer and in other words, an oxidizing agent and something that can get oxidized very rapidly. The idea is that you have to generate a lot of heat and a lot of gases. So many of these explosives such as RDX, they contain nitrogen and a lot of oxygen. What happens is that it can generate either nitrogen oxides or carbon dioxide in a very short period of time, and that is what causes the explosion. But as far as your specific question is concerned, I would not know. The forensic team which have investigated this, they probably have figured it out. But typically these things are not shared with the public.
Thank you, sir.
Thank you for asking the question.
There is one last question we can take,
Yeah.
I think. One last question before the tea break. Sorry, one second. anyone else who has your questions, don't worry. Professor is around. He will have a tea break with you. When you're outside,
Sure.
you're welcome to ask your questions, okay?
Sir, why is it so that we can't determine the position and the momentum of the atom at the same time as Heisenberg stated it? And then how did Schrödinger founded the probability through his wave equation?
Okay. I will try to answer the question because, sit down, because this is a little bit more on towards physics. For small, this position and momentum that applies to the location of small particles only. See, if you are trying to observe something, how do you observe? How do you see things? That means that I'm shining this one with light, and the light interacts with the matter, it is reflecting it back to me. Either I see the same light or absorbed light or emitted light. That's what my perception tells me. For example, I'm seeing this object, okay, because there is light, right? Without light I cannot see. Because the light falls on it, some of it is getting absorbed, and I'm seeing it in the reflected light because that light reaches my eyes, and my eyes have retina, so that creates that image. So that's how I'm seeing it. So this is a large object. So when the light falls on it, the energy of the light is not enough to move it. But when you're looking at small particles such as the electron, if I try to observe an electron with a light, the light carries enough energy to make the electron move. Okay, and that is why I need light to observe it, right? But when I shine it with light, it starts to move. And therefore, I cannot get its accurate position. Okay, that's a very simple way to explain it. But as the objects become bigger and bigger, I can definitely see them. For example, in electron microscope, you can even see atoms, which are part of a fixed structure. Again, if it is a gas molecule, I won't be able to see it. It will start to move when I shine it with light. So the light energy has enough energy to make the particle move from its original position. So therefore, I cannot see it. Okay, this is a very rough explanation.
Thanks, sir.
Okay, thank you very much, sir. And it's time for vote of thanks. Before vote of thanks, and I would like to request Professor Shiba Vasu on the dais, and Nandita and Simfa and Professor Uday Maitra, please come on the stage. Just a moment. Yeah. I request Professor Shiba Vasu ma'am, Chair Education Technology Unit, hand over a small token of gratitude from JNCASR. Yeah.
Thank you. Thank you very much.
And this is for Simfa. And Nandita. And sorry, I forgot to give these books. These two books from Professor CNR Rao for you people, and I told them, okay, you people are coming with Professor Uday Maitra, and he suggested to give this Climbing Limitless Ladder book, and this is for you, and this one is for you. Thank you. And one more book, this is for Professor Uday Maitra. Madam, please hand it to you. Yeah, please.
One more.
Thank you. Yeah. And this is a small token of gratitude from Mrs. Indumati Rao, Administrator, CNR Education Foundation, to Professor Uday Maitra. Thank you.
Thank you very much.
Yeah.
It was really not necessary.
Yes. Yeah. Thank you.
Thank you. Picture for all.
Yeah, we'll take that chemistry photo. And the online participant, please be online. And there is an announcement. Yeah, please scan this QR code. And I request the coordinator or the principals, please, the coordinator of JNVs and joint commissioners, please share this QR code to all the schools and colleges. And we need a feedback, and we are going to host another program that is a Physics is a Fun in next upcoming program. Okay, please scan this QR code. Okay, be online, and I'll give a vote of thanks. Just we'll take one photo in 2 minutes, and I'll come back online. Please be online. Please don't disconnect. Yeah.
Yeah, and can I suggest that all 5 of us come
Yes,
there,
yes, yes,
and Praveen,
we'll
you
go.
come here,
Praveen.
take a picture from this
Praveen,
side,
front you go.
and all of you do this
C.
C for chemistry. Make
Okay?
sure that it is not ulta.
Focus ಮಾಡಿ telecast ಮಾಡಿ camera photo click ಮಾಡ್ತಾ ಇರೋದು. Okay, if possible, all online people, you can switch on your the camera and ಬರ್ತೀವಾ? ಹಾಂ ಮಾಡು ನಾನು ಸ್ಟಿಚ್ ಮಾಡ್ತೀನಿ. Okay guys, listen, don't make noise. Okay,
Noise will not be recorded.
noise will not record and not come in the photo. And yeah. And don't shake your hands because you will take a half photo, okay? 2 photos and I'll merge it later, okay? Don't shake, okay? Statue.
Okay, show your C, because if you don't show your C, you won't get G. Okay, ready?
Yeah.
Ready? C for T.
Thank you.
Thank you very much. Thank you.
Thank you guys. Be online. Now it's time for vote of thanks. It's time for vote of thanks. Okay. On behalf of CNR Rao Hall of Science and Education Technology Unit, I sincerely thank everyone who made this today's program success. Particularly Professor Uday Maitra for inspiring and engaging session filled with a wonderful demonstration. One more time, big round of applause for our entire team. And Professor Shiba Vasu ma'am, Chair Education Technology Unit, for warm introduction and continued support. My deepest gratitude to Bharat Ratna Professor CNR Rao, FRS, and Dr. Indumati Rao for their vision, guidance, and lifelong commitment to popularize science in India. And you have already saw Professor Rao, he was in online, okay. And thanks for coming online. And yesterday I requested to Professor CNR Rao, so we are going to conduct a program throughout the country, and he agreed. Okay, I will come online and I'll bless them like that. He said. Okay, thank you to him, and my sincere thanks to Professor Umesh Wagmare, President Jawaharlal Nehru Center for Advanced Scientific Research, for his support for providing infrastructure facilities to host this event. My gratitude to Administrative Officer Joydeep Deb, JNCASR, and his continuous support. I have to thank this and the Jawahar Navodaya Vidyalaya Samiti for enabling nationwide participation, especially Joint Commissioner Gopal Krishna, former Joint Commissioner A.N. Ramchandra, Ms. Meenu Singh, and Dr. Vinita Kumari from DST Science and Technology Capacity Building Division, and Dr. D.K. Modi, Senior Consultant Vignan Jyoti, the scheme. And I thank all the the team of Jawahar Navodaya Vidyalaya Samiti, okay, JNVs, all the Vignan Jyoti program, the principals, and my respectful thanks to participants, teachers, and thousands of students. More than 300, I just observed, more than 300 teams participants were there. That is a 1-1 school. Each participant is a 1-1 school, ma'am. And 300 YouTube, more than 300 YouTube, the viewers were there. That is one YouTube viewer is, one school, we consider like that. And thank you all, across India, all the JNVs. My special thanks to you, and in person you are participating, that is the Jawahar Navodaya Vidyalaya, Bengaluru urban students. Okay? And finally, I thank administration, technical team, Dilip, Prabhu, Praveen, and Bhuvan, and AV team, and for their dedicated support for ensuring, checking all the event, because this is a big event, that's why, since 2 days we were checking, the technique should not have any technical glitches. So anyhow, it got the good the response. Thank you very much, technical team. And thank you all for being part of this national outreach initiative. With this, we conclude the today program. Participants present here are kindly requested to remain in a group, and we'll go and have a coffee and tea. And online participants, please, ask your teacher or coordinator to scan this, the feedback form, and please kindly fill this. And if you're still online, okay, fine. What I'll do, I'll share the video teaser, next program video teaser to all the JNVs, and I have all the email IDs of JNV. Thank you very much, and staying with us. Thank you once again. Have a wonderful day.